So we should start on that, right? Very good. Good afternoon. Now we are all energized after lunch, and we can start the second session today. The first speaker will be Ben Clark from MSU, and Ben will tell us about emulating the Magnus formulation of in medium SRG.
All right. So hello, everybody. My name's Ben, and yeah, I'm going to be talking about emulating the Magnus formulation of IMSRG. So just to give an outline of what we're going to be talking about, we're going to be talking about what is IMSRG and why we need this type of emulator, how our emulator works, and then we're going to get into some results. So just background, what is IMSRG? So IMSRG is a method to basically continuously apply a unitary transformation to a Hamiltonian to make it in a basis that's nicer for you. So maybe that means band diagonalizing or block diagonalizing, as it is. As you see in this picture, you have a block diagonalized Hamiltonian. And one of the reasons in medium SRG specifically is really nice is because it can do this while working on the operators themselves, not working in the many-body space, which is very expensive to build. But in principle, what you're actually doing in order to apply this continuous unitary transformation is, well, the laser broke, but there's you're just solving this differential equation over here on the left. And what you have to do in order to solve that differential equation, you have to compute a lot of commutators. And the computation at IMSRG2 level, so just taking the two-body forces, the computational complexity of doing that is roughly n to the 6, where n is the size of the single particle basis, which is, I mean, it's good because it's polynomial, but you know, if we can reduce the amount of steps that we need to take, that's a big plus. It's also important to, oh, thank you, Dean. Yeah, okay. It's also important to realize why exactly we're doing IMSRG. So a lot of times, you know, we work so hard to get this new basis, this unitary transformation. We want to be consistent with our other operators. So you want to put your other operators in that same new basis. And in order to do this, you either have to double the dimensions of this differential equation. So you have to solve for your Hamiltonian and a different observable at the same time as well, which just doubles your problem size. Or you have to keep all these generators that you use so that you can then kind of evolve this for your other operator. And as you might imagine, that's a lot of work. And so instead of doing that with what's called the direct flow version of IMSRG, you can use the Magnus formulation of IMSRG, where it basically assumes a form of your unitary transformation. So it was just implied before in the differential equations. But with Magnus, you assume that it has some form, which is e to the omega. And now you're solving this differential equation here for omega. And this is really nice because since you know the form of your unitary transformation, you can just save it and you can apply it to any other operator that you want. So you only have to do solve this differential equation one time and then save your answer, and then you're good. So it makes this part in your workflow less work. So this is the version of IMSRG that we're going to focus on emulating in this talk. Before people have tried to emulate the direct flow version of IMSRG, a grad student that was here at MSU before me, his name is Jacob Davison, wrote his thesis on this, largely on this, and he was using dynamic mode decomposition to emulate the direct flow of IMSRG. And as you can see, so this is a graph with your energy as a function of your flow parameter S. And what you can see here is even if you just get very early training data, like the first 5–10% of the flow, you can predict the energy as a function of S pretty well. And you can also see that even if you don't take lots of training data, it doesn't really improve that. Like, it's already pretty good, but even if you take more training data, it doesn't improve that much. So what that means is using very little data, we could kind of forecast the flow of IMSRG pretty well for direct flow. And it works great. I mean, it's had simple implementation, trained fast, and it was pretty accurate. However, dynamic mode decomposition does not work for Magnus IMSRG. So this is a plot trying to do kind of the same thing here. But this is the difference in your energy as a function of S, right? And you can see that even if I give a lot of data, like the first 10%, 20% of the flow, it still diverges if we try to extrapolate at all. And that's a problem. So we're trying to find a new emulator that will work for this problem. So what we did in order to try to solve this is we turned to parametric matrix models, which there will be a lot of talks on tomorrow. But if you haven't heard of PMMs, it's just a machine learning method where, like, instead of a neural network where you're learning weights and biases, you're learning elements of a matrix equation, matrix elements. And this is nice because you can train on things that we use a lot, like eigenvectors and eigenvalues. So what we do is, so in practice, when we're solving this differential equation, we vectorize the elements of our operator, and then we plug this into a general ODE solver. And basically what we do is we just try to model this this vector as a function of your flow parameter S. We try to model that as a sort of, you can think of this as a time-dependent Hamiltonian, but it's just a matrix problem with a dynamic part. And so we model this vector as an eigenvector of this problem, the ground state eigenvector of this problem, and we train on a loss function that basically measures the overlap between our emulated value, our emulated vector, and the actual vector. So it's not just completely black box. It includes a little bit of what we know about the characteristics of IMSRG. So here, this Y of S, which really encodes the dynamics of IMSRG, it's fit to a function that's from the perturbative expansion of IMSRG. And so it kind of has this functional form where you see a bunch of 1 minus e to the somethings. And we can use that fit to try to extrapolate the norms of the vector, and that can actually help us train quite a lot. And we can use that and its derivatives to get physics-informed emulation. Okay, so now we're going to talk about some results. So a lot of the stuff that I'm going to show you right now is from the pairing model, which I'm sure a lot of you have seen, but just so that we get our terms straight, this is what I'm using for the pairing model. This is what I call the coupling constants, but we also add a pair breaking term to make it a little bit more realistic. And we call that B, and you'll see me interpolate that later. So when you see an interpolation, just know that I'm interpolating this part. So in order to test this thing, we wanted to see, of course, if it's actually working. So this is a correlation plot of the matrix elements of the Magnus operator. And what we did is we trained it from the flow parameter S equals 0.4 to S equals 2.3, and then extrapolated out to S equals 10. You can see that you have a nice straight line for this correlation plot. So it looks like it can get the steady state final values of the IMSRG flow off of just a little bit of data. But we also wanted to see if it was getting the dynamic straight, like not just seeing if it could get the final answer, but if it actually kind of understood the IMSRG flow. So since we're using a toy model, we could make this GIF right here. And so what this is the 0 body, 1 body, and 2 body operators respectively. And here you can see this is the actual IMSRG operators, and these are the emulated operators. What you can see is the PMM actually understands the S dynamics of IMSRG pretty well. The operators pretty much match each other throughout the entire flow. And as I said earlier, the reason we're interested in Magnus IMSRG is to compute other observables. So this is just the spin squared operator for the pairing model. And we can see that we also get a nice correlation plot. We see that our emulated results are lining up with our original results. And we also want to see if we can interpolate, because that's an important thing if we want to do things like error analysis in the future, uncertainty quantification. And this is just using a basic RBF interpolator from SciPy, and just getting 5 data points. So this is the training data here, and these are the different values that I extrapolated out to here. We can see that the interpolation works pretty well. But what about for real interactions? I'm showing you all this toy stuff, but we want to do some real physics. So even for realistic interactions, which we started doing this year, it still works out pretty well. So this is for calcium 48 at Emax 14 using only 19 training points. We also get a pretty good correlation plot. And this is notable because this is 18 million parameters We were modeling with about 1,000 parameters with our PMM. And again, we're mostly interested in transforming other observables. So this is using this Magnus operator to then transform our Hamiltonian. We can also see that we get a really nice correlation plot. So results look really promising. Hopefully we'll have better metrics on exactly how well this is doing, but you can see that this is more or less predicting the behavior pretty well. All right, so that's really all I had to say. So it seems to work pretty well. Future work, we want to figure out some robust methods for multi-parameter interpolation. Fortify our fit accuracy. Sometimes that fit that we have to do, sometimes it can deviate a little bit. It's right about 95% of the time, but for that 5%, we want to figure that out. We want to apply the same thing to open shell nuclei, and then use all of our tools to do things like UQ and global sensitivity analysis. So thank you.
Thank you, Zhang. Questions? Ready?
I don't want to take you too far off like your specific work, but I guess I'm really interested as to why like DMD doesn't work for the Magnus IMSRG specifically. Do you have any insight as to why it fails in that use case?
Yeah, so one of the simpler answers is whenever you do normal IMSRG, your snapshot vector is a non-zero vector, like it starts high and then it goes low. And then for Magnus IMSRG, it actually starts at 0. So at flow parameter s equals 0, your Magnus operator is 0. And so that can be an issue just like numerically from a very basic perspective. And if you look at this graph trying to do the same thing with DMD, actually if you take a graph where you start at like s equals 10 to s equals 20, if you train on that region, you can then get kind of decent results. Still not great, but that can get rid of a lot of the numerical issues. Also another thing, so DMD, it gives you it basically assumes that your underlying mechanics are linear.
Yeah.
And with PMMs, you can kind of bake in some nonlinearity, because even though the matrix equation, is only dependent on S in like a linear way, the eigenvector doesn't have to be. So you can kind of bake that in.
Awesome. Yeah, the linearity versus non-linearity is what they usually talk about when applying DMD. So that makes sense.
Yeah.
Thank you so much.
Yeah.
Okay.
I was curious, so you mentioned UQ's future work, so maybe I shouldn't be asking about it. But I'm curious, when you're predicting an operator, what does UQ look like? Are you looking at error bars on each element, or are you only caring about UQ for the final energy prediction?
Oh, yeah. So the UQ, from my understanding, is mostly looking at basically doing interpolation for different LECs or different parameters of IMSRG, and then using that such that we can kind of generate data faster so that we can do UQ on things like LECs.
So it's not emulator UQ,
No, it's not. Yeah.
Yeah, I'm just curious about the your model and the architecture of the model. I don't know if you have some insights of the complexity of the model you're trying to use to what you're trying to model. In other words, is it the complexity of your model too little or just about right for where you're trying to emulate?
So the complexity, are you talking about the complexity of IMSRG or the complexity of the emulator itself?
There and the whatever model you're trying to use, not the energy.
Not the what?
So there is right now, right, the big question of machine learning and AI, which is sure you have a lot of data, and the data can be generated from whatever theory, right? But then you apply any machine learning model, could be physical constraints or whatever. But then there is a way now to quantify how complex the machine learning model, let's call it, is compared to what you're trying to emulate from the physics or whatever reality it is. And the idea is that if you have a model that is too simple, right, you're going to get a lot of results, but the complexity is not going to get to what the physics you're trying to model.
Yeah.
And vice versa, right? If you're trying to use a too complex model for a very simple physics problem, you are going to use too much of computer power for something that is not needed.
Yeah.
In other words, so I don't know if there is some insights from quantifying that part.
I see what you're saying. Yeah. So the thing about PMMs is it's kind of automatically like a physics informed thing. So it can kind of get rid of a lot of complexity that you would deal with like a multi-purpose, like a neural network. So I would say that the nice thing about this model is it kind of uses what we know about IMSRG. to kind of give it a head start on its training data, so it doesn't need as much training data. So, I mean, I don't really know how this stacks up, but people have tried to do similar thing to what we're doing here with like neural networks, and they need a lot more data and it's a lot more training parameters. And this has a lot less training parameters. So I'd say as far as emulating this goes, this is the least complex model to do this problem that I've ever seen.
Just a comment to that. Probably what you can do is you can use different dimension of your camera, right? From A and so, and then that actually mathematically increase the parameter and increase the complexity of the problem. From that you can have information and which one is the small model you can capture.
Oh, that would be nice, yeah.
Yeah, that's true as well. So normally the amount of data, like the least amount of data you need to use, you really need to get this fit right. So far, the least amount of data that I've been able to use is whatever little amount of data I can use and still get this fit right. And I found that somewhere around S equals 2. So however many training points that is, sometimes it's like 30 training points, sometimes like 20 training points, but you really need to get this fit right. And then after you get this fit right, the PMM kind of finds the minimum pretty quickly.
I have a pretty simple question. You said something about 8 million down to 1,000. Explain what you were talking about there. I just didn't catch.
Oh yeah. So so the PMM, you know, it does this. So this matrix problem that you're learning, it does it all in a reduced space. So you build a projector and you do it in a reduced space. And what I can see is sometimes these Magnus operators that in reality are like 18 million matrix elements, I can project down to about 1,000 matrix elements. And
So it's matrix elements, not this index you have up on your expansion.
Oh yeah, yeah, it's matrix elements. So this just means 0, 1, and 2 body piece.
Okay.
But the 2 body piece could be like a few million matrix elements.
Gotcha.
Yeah.
Now, no more questions, so let us thank Ben again. Could you tell us? Okay, super. Now, Dick will give a joint talk with Xilin, who is unfortunately not here today. And the topic is update on continuum emulators and neural quantum states.
Let me raise this screen.
So since the previous talk was faster than expected, and Dick says he's not going to use 30 minutes, we suggest that we'll move Bryce after Dick, and then we will finish a bit earlier.
Okay, so this is just a few slides from Xilin. He had a family emergency, had to go back to China, and didn't have time to even put together his talk. He's doing many interesting things. So this is maybe a little advertisement of some of the things going on. Okay, so he put this here. Only a quick update. Okay. And one of these things is about nucleon deuteron scattering emulators. There's a lot of emulator work that's been done. There's a couple of papers that are under review right now. So this is using reduced basis methods that we've heard, and then in particular also some active learning. And Abhinav and Christian will talk about things related to that. And I think maybe Christian will touch on some of this particular work. This first pass at it is below deuteron breakup. So that's going to mean very low energy, and it's not actually the energy regime we'd be most interested in for the application here, which might be to fit 3-body chiral EFT constants. So going above the breakup threshold is what is particularly interesting. And so this is just an update that things are happening there. are you going to talk about this at all?
No, not at all.
Not at all? Okay, well, there's not a whole lot to say, other than, this is a region where you want to sit. The structure of everything, that is being done, is the same, and things are possible. So that's one piece of work, in progress. Another one, which we heard about at the nuclei meeting earlier, this week, has to do with doing linear response in density functional theory. And the idea here, as in some other work that Xilin is doing, is that you're emulating in the excitation energy here. Okay, and you may generalize for emulating in other parameters. So you do snapshots at certain values, and then you can go to other values. And an advertisement for a paper in preparation. Another one is neural quantum states. So again, here trying to look at excited states rather than ground states, and this is using another subspace projection method to do this, working at complex energies, as we heard earlier today with a different method, and you using the neural quantum state approach here to get some complex energy solutions. Then that becomes a basis for the space, and then you compute the spectrum, diagonalize in that space. Okay. Currently, these are results. I have no idea what to do with those, so there you go. I assume this is with Ali Lovato. I'm not actually sure who else is on that project. And that's it.
I'm not sure.
You want to ask me questions about things? Go ahead.
But you are welcome. It might get entertaining. Yes, any questions to Dick slash Xilin?
I can pass things on, by the way. And
So neutron scheduling.
Yeah.
Those are sort of elastic scheduling, right? Or
Below
Yeah.
the threshold.
yes, so you're not breaking up the deuteron.
Yeah.
On this, yeah. So there is, some free body things happening, but this is below a couple MeV, right? So
Very low energy.
where you might want to sit, might be in places where there tend to be a minimum in the 2-body part and the 3-body. So there's particular kinematics people like to look at to fit things. Okay, and then the idea is these are expensive calculations because they're 3-body, and you want to be able to do them faster. Okay, to do a Bayesian sampling of this.
Sorry, not a direct question because, of course, I don't think you were directly involved in the strength function paper. But I was talking a little with John Engel yesterday or the day before.
We're talking about this.
Yeah. And one of the things that I mentioned, so just to pass information to Xilin, when we were trying to use reduced basis for at least the strength functions that Ante and Gordon were playing with, it didn't work very well because the things were moving kind of left and right, and having a linear embedding of bases didn't work on something that kind of moved left and right and decomposed.
I'm not quite sure what left and right means.
Yeah, sorry. So if you think of the strength function, and you're changing the parameter, if you look at the plot, it doesn't look like something that is splitting. It looks like you have peaks, localized peaks.
Okay, and that's what you mean left and right.
And then when we were trying to make that work, we ended up needing so many reduced bases that the thing didn't work very well, as if you in comparison to when you're doing like scattering. And what ended up working for us was to parameterize the thing not with a reduced basis, but rather with localized Lorentzians. But then we were having trouble. How am I going to project the equations or get the equations functional? And that's what led to all the things that Lauren will talk about tomorrow. Could be useful to, if they are having the same problems as us, maybe they didn't, maybe their linear response is different. But it could be useful to have conversations. And I really thought that Xilin knew about this approach, but I haven't talked with him about it. I definitely talked with Jonathan and he find it. That's my goal. You know?
Okay, sounds good. So something to pass on. So since Xilin lives here, you
That's-
could probably
I know.
do it more directly than me.
But I didn't even know.
Oh, and I didn't actually say, by the way, so there was a medical emergency. Things yesterday looked much better.
Okay, that's very.
I should have said that first, I'm sorry.
Okay, well, let us thank the. So Bryce will tell us.
Yeah.
Thank you very much for agreeing to give
No
your
problem at all.
portfolio. Medium mass nuclei with neural quantum states.
Yes, so, Bryce Fore, I'm a postdoc at Argonne National Lab, and I'm going to be giving a very basic overview of what neural quantum states is, as well as showing off some of our recent results in medium mass nuclei, or at least towards medium mass nuclei. So the problem that I'm discussing here, and I think most of us are discussing, are the nuclear mini-body problem. In particular, I'm looking at continuous position space. We have spin and isospin dependence. And this is specifically the time-independent Schrodinger equation. I'm only looking at ground states. At least everything in this talk is only about ground states. This is the method I'm going to be talking about is equally applicable to nuclear matter calculations, and we've done those before, but the results I show are just for nuclei. There are many good methods of solving this exact problem I'm describing. It's been thought about for many years. Here's two examples. Most of these, though, come with some source of dimensionality, some problem by which everything seems to scale exponentially, and it makes it really hard to get to larger and larger systems. The neural quantum states, which is effectively just using some architecture of neural networks to represent the wave function, somehow gets around this by being able to represent very high dimensional functions effectively. So these other methods are exploring maybe the entire Hilbert space essentially, whereas the actual physical states that we care about only occupy some small region of that Hilbert space. And somehow the artificial neural networks, because they're so good at representing these complex functions, hone in just on that region. This little picture here is just representative of what's happening. We're passing in the spins and the positions and getting out a wave function. This is not really what the architecture we use looks like at all. The scaling of this system, you might ask, if it's not exponential, what does it look like? So conventional variational Monte Carlo methods are some exponential, but our worst case is really something like the number of particles to the 5th power. And additionally, on top of that, the scaling with resources is actually nearly ideal for most of the algorithm. We can see the total time here as we go to a very large number of GPUs slightly deviates from ideal scaling. But that gives us a huge advantage as well, since this algorithm is almost essentially embarrassingly parallel. So what is the actual algorithm? Well, it's almost identical to variational Monte Carlo, which I'll describe a little bit in case nobody's heard of that. The basic idea is we define some family of wave functions. In the case of neural quantum states, that's some neural network architecture. In other systems, that's some much simpler setup that's physically inspired. But in general, we have some family of wave functions. We then, given some initial wave function out of this set, will sample it with configurations that represent our system. So say I'm looking at 16 oxygen, then I'm producing positions and spins corresponding to the particles inside 16 oxygen, all the neutrons and protons, that represent that system for each configuration. And I have thousands of these configurations. Averaging over these allows me to get any sort of observable that I can calculate this way. In particular, though, the energy, where we can then use simple minimization techniques, or I won't mention them, but we use slightly more complex techniques for the neural quantum states to essentially minimize that energy that we get with respect to the parameters of our wave function. The important point here, though, is that as we're doing this, in order to have this condition of our measured energy is greater than the ground state energy, we have to satisfy the variational principle. And all that is going to mean for us is that our wave function satisfies fermion antisymmetry. That's all that's required for us for nuclei, at least, to have this. So as we're repeating this loop of sampling and minimizing, we won't ever get an energy below the actual ground state of the system. So this serves as like an upper bound. To go into a little bit of detail on the actual potentials that we're looking at, we're starting with just some very minimal potentials that represent nuclear systems. So here, this is a leading order Pineless effective field theory Hamiltonian, which is the first thing we started off with. Don't need to worry about all the equations on the right if they're not familiar to you. This is more for the people who've seen this stuff 100 times. Effectively, we have 2 and 3 body interactions. Our 2-body interaction includes spin and isospin dependence. The thing I want to point out is that the 3-body potential here is just fit to 3 helium binding energies. And this potential on its own, we've used for quite a bit of time. We've used it for nuclear matter. We've used it for nuclei, and it works pretty well for light nuclei. We get energies that are pretty close to what we would expect. This is mostly just testing the method, as well as looking into how minimal of a potential we can look at without having to write out the most complex thing we can find first. But as we move to larger systems, we can see the energy is not fitting nice, not just dead on anywhere, 16 oxygen's a little bit of an anomaly, but that's fine. Anyway, we realize we need some slightly more complex potential. So instead of just going full in and adding everything we can, we're looking at just adding a few terms at a time to see what kind of effects they have. In particular, we have 2 potentials that I'll be showing, which I just call the charge-dependent potentials. They include charge-dependent and charge-asymmetric terms, various electromagnetic terms beyond the simple Coulomb interaction between protons, and importantly, we take the 3-body potential, and instead of just fitting it to 1 small nuclei, we fit it to 4 helium and 16 oxygen binding energies. And I do that fit manually by running this system with multiple different parameters for the 3-body interaction. There are 2 potentials that I'm going to show that use this setup. One is I just call CD, and that's everything I just described, plus the original one, the leading order Pineless potential. And then the other is this CD triangle, where I instead have this 3-body interaction that includes all 3 of the pairwise distances in the triplet instead of just 2. Ultimately, this didn't make much of a difference, but it's in the results, so I show it here. We have 2 more potentials, which are just like the first one, but have p-wave terms included. This is just additional 2-body terms, and I again have this 3-body potential that's adjusted to 4 helium and 16 oxygen. Gadavigo et al. Looked at this potential already. At least the 2-body version is exactly like ours. So we took their range of V11 values and just looked at the weakest and strongest ones that they included to get some sort of range on this potential. Finally, some results from the actual study. First of all of these results start off with some completely random neural network, which is horrendously, if you look at this blue curve, starts off horrendously above the actual ground state value. As we train and go through this loop, we get very quickly something much closer to the actual ground state. And it's really all the results I'll be showing are just some average of the last few steps of this where it's no longer changing and we have something that's converged. We can see if I compare this to the green curve, the green line here, that's a variational Monte Carlo result that doesn't use neuroquantum states. We very quickly pass that. It's when you're looking at this AFDMC curve, it's important to note that AFDMC is a method of improving this variational Monte Carlo result. Our result is also just variational Monte Carlo, so very reasonably you might just ask, why don't we use DMC to improve our result? And the answer is we're working on it. None of the results here use that though, so we just have the variational Monte Carlo result. And finally, we actually get to the larger nuclei results. So these are binding energies for a variety of nuclei. There's a lot of information here. Essentially, each of these dots is the result for each of the potentials I was talking about. Each of the lines is the ground state value for experimental results. Not that that's exactly where our system would actually have a ground state energy. But we can see we've done pretty well. This is expanded out since I took off this lightest nuclei. It looks a little worse, but the triangles are in the same position as they were on the other plot. Of note, maybe we explore the oxygen chain a little further here, and the calcium chain as well. We can see both of those seem to be underbound as we get farther from stability. Additionally, these, as I said, these CD and triangle potentials kind of just lay on top of each other. So impressively, that didn't make much of a difference. We also get lots of other observables. So just as an example, the radius of the nuclei are shown here. Again, a lot of information. Could stare at this all day, I'm sure. But some things to point out. For larger nuclei, this weak P wave potential does seem to do quite a bit better than the original pionless potential, in some senses at least. Other results and a caveat of sorts, we can look at the angular momentum of these nuclei, where the expected values are in the second column and our measured values are in the last column. And most of these line up very well. We have very big difference here though with oxygen 17. And the issue is that 17 oxygen has a ground state with a L squared of 6, but another low-lying state very near it with something like 0 L squared. So what we think might be happening here is that we're getting some mixed state between these. But we're working on separating this out, seeing exactly what's happening. And that's something we can investigate with this method. On the right, you can also see I've explored the neutron skin radius for 48 calcium. Relevant since here I have the C-Rex experiments value. Obviously, our original potential is very far off, as well as our charge-dependent ones didn't have too much of an effect. But the P-wave potential modified this significantly. Can read into that as you will. Finally, though, on the topic beyond the potential, the method itself, scaling is incredibly important. As I showed before, we have very nice scaling with number of devices. And as we look at the actual scaling, we see empirically, instead of what we would guess it to be, it's really something closer to like A to the third, at least for these minimal nuclei, and maybe a little higher, like less than A to the fourth, but somewhere around there for these larger systems, which is very nice scaling compared to potential other methods. If I just take that scaling and look at what I can reach with the computers at Argonne, everything we've done has been on Polaris, and we're around this point on the nuclear chart. If we use the whole machine, we can maybe get up to A equals 63. If we're able to move on to a much larger machine like Aurora, we can potentially get as high as like 123 nucleons. With this, the ab initio system is pretty nice. Some conclusions. This is working for various fermionic wave functions, very nice scaling. We still need to work on the potential terms, of course. Some things that we are working on, I mentioned the diffusion Monte Carlo calculations starting from these results, as well as potential excited state calculations that are in the works. Some collaborators at Argonne, Alessandro Lovato and Jane Kim, and Morten Help Jensen at University of Oslo. Yes.
Thank you. Very good. Yes.
Hi, Bryce. Great talk. This may be a misconception on my part, but in following NQS stuff, it seemed like for a long time we were at like a cap as far as size goes of like oxygen 16, and the goal was to push on to calcium 48 larger nuclei. Now it seems that we're here. What was kind of the bottleneck and challenges there that made jumping from oxygen 16 to larger nuclei difficult? And do you foresee any challenges beyond? I mean, you had the slide about the computation resources needed to do it. Do you see any other kinds of challenges that might come up as we start to go to larger and larger nuclei?
So the reason we weren't presenting things beyond oxygen 16 that you would have seen was really a lack of one computational access, resource access. So having more time on large computers helped quite a bit with the nice scaling laws. But also the potential, using this original potential didn't work very well. So we wanted to work into exploring that. The next term that we think is going to have a very large effect are things like tensor terms, which previously we actually couldn't include for, I can go into it later if you'd like, based on
about that,
the way we were conserving isospin and spin.
I see.
So we couldn't modify that, but the term requires it. But now we actually have that as a possibility.
Gotcha. Or interesting.
More questions?
Yeah.
Yes, I do.
So should I view the A cubed scaling as a consequence of the short range force? Or is it?
The A cubed is coming from our anti-symmetrizer in the wave function. The potential so the A to the fifth in the worst case scaling is coming from the potential calculation being A squared and the anti-symmetrizer the wave function itself being A cubed, and we have to run those together. But that A to the fifth has a very small leading term, so we don't see it yet, essentially. So it's A cubed at the moment at this scale because of the wave function calculation.
That's not an impressive result. So I'm wondering, is that difficult to put more symmetries in your function? Maybe SO3 is kind of difficult, but how about the parity, right?
So we actually do include parity. That one's pretty trivial. Other things, we've included other symmetries as well. Not many have made as much of a difference in the sense, like we can just train a little bit longer and it reaches the same value. So we have played with adding symmetries, and I can certainly enumerate them for you later if you'd like. But it hasn't had a lot of effect beyond adding parity.
Very, very nice work. I had a question about the thing you were having trouble with the oxygen 17.
Oh, yeah.
Yeah, is that because the spin orbit splitting was not enough and you were mixing in some S states and something?
Yeah, so we think, I'm investigating this as like currently. So we think that there's, some low-lying L squared equals 0 state in the actual system, in our system. Maybe in our potential, it's actually lower. Maybe it's not split at all, and we're just getting a mixed state here. It's not clear yet.
Okay.
Like,
I have two questions. So first one is like, can you guys do things like break a symmetry and then restore it at the very end?
Yes.
Like,
Yes, yeah, we've actually, yeah, so that's actually something we've done, and that's how I'm investigating this issue with subtene oxygen. We have a paper fairly recently. I don't think I have a link to it. I don't know. Maybe I have. Let's see. Hold on. Got a bunch of slides. There we go. So we can add in something like a magnetic field or a coupling to elsewhere, and let that break the symmetry and then turn it back off at the end, essentially.
and then the second one is you showed your nuclear chart with like where you think you can your estimates of what you think you can reach from different machines. Can you just give us an idea of like how you think that graph is going to change as your interactions become more sophisticated?
I mean, they'll be lower. Our limits are going to be lower if we have harder compute interaction. Beyond that, I don't know that I can give any more details.
Okay.
Yeah.
Okay, I have a question too.
Yeah.
Could you go back to this previous slide with calcium 48 results?
Oh, the skin? Yeah.
Yes, so first of all, there exists data on charge radius
Yes.
of calcium 48.
Yeah, this is the C-Rex result at least.
No, forget about series.
Oh, okay.
I'm talking about RP.
Oh, sure.
So proton radius is related to charge radius.
Yes.
So you can get good information about the proton radius from very precise experiments.
Yes.
And this is based on Mr. Google, 3.47 is charge radius.
I have not included that yet.
The corrections should be added, of course, but you can immediately use proton radius as reliable data. C-Rex is not reliable, and I would like to warn.
I was not attempting to compare two C-Rex as a reliable result. I agree.
Is not experimental data. So experimental data are proton and parity violating asymmetries. This is not a data.
I agree.
So I would say, let us concentrate on proton radius. There are also nice data on neutron radii or matter radii from Tanaka et al. From Riken experiments.
Okay, if you could send me references to that, I'd like to include it here. This is just what I had in our paper at the moment.
Yeah, so send me an email, I will send you the.
Sure.
Okay, very good. Yes.
Sorry to drag this out even longer. So your estimates on the limits of the nuclear chart can go, is that just based on the peak flops of those computers?
It's based on this scaling and the number of GPUs that I used for the largest system.
Do you expect this graph to actually be in terms of number of physical cards or in terms of the flops of them? Like if we jump 10 years in the future and every GPU was 4 times as powerful, do you think?
Oh, then this would go farther.
Okay, so it is.
This is not flops based, it is nodes based. My calculations. This is, but I mean, also they're not going to be replacing on these particular computers anything, so.
Sure, but that. You're saying that more powerful GPUs wouldn't improve.
Would improve it. Yes.
It is flops.
Yeah. Yeah, sorry. My plot here is not flops based.
Sure, yeah.
But I agree, it would improve if you had a better GPU. If you had the same number of GPUs, but better, it improves it drastically. We've looked at, most of our calculations are A100, but we've looked at the newer NVIDIA and they're much better.
So my actual question was actually, have you looked at Google's TPUs? They are.
We haven't had access to any of those.
Nobody really does. So.
Thomas.
This scaling is so much more favorable than anything else I know. Our cluster is much more expensive. No problem in mass 100 or mass 150. So I wonder, where does this come from?
Where does the scaling come from, or?
No, why do you limit just, why do you estimate that even with Aurora only mass 100% nuclei? Why not the full charge?
So I'm not maybe knowledgeable enough about how coupled cluster gets to larger systems.
So it's A squared, but then the number of single particles stays to the 4th power, and that can be as large as 1,000.
Okay.
So so this is a very advantage scaling from my point of view.
Right.
And as an OSCF, there's no problem for us computing mass 100 nuclei. I know, or is there a gigantic effector in front of that?
I guess, I mean, we're computing every nucleus, every nucleon in the nucleus
Yes.
individually, right, with their motions and things in a Monte Carlo formalism. I think Monte Carlo itself, prior to this variation of Monte Carlo, was at like 16 oxygen.
No, your progress is tremendously impressive. I just wonder, this is hardly Ford must be more expensive for us than A to the 3. I just wonder, that's all.
I think we might have to compare later to figure out where the discrepancy and how far each one can reach is. That is not clear to me.
There's been great progress in calculating heavy nuclei in such approaches as Thomas showed, as Bryce showed. I would like to see ab initio mass table, mass table obtained from realistic interactions that I would use in our model mixing calculations together with, sophisticated DFT results to get such an ab initio mass table would be very, very good.
Yeah, so that's what we're working towards is ab initio with more realistic interactions as we include more and more realistic potentials.
Okay. There are no more questions, so we'll have coffee break now. Let us think about it. Coffee break, and we'll start at 3:30 for Morten's presentation.
The coffee may not arrive until 3. You might need to wait a minute.
Which will be 7.
When do we take the picture?
Oh, yeah, so why don't we actually use the time before the coffee to take a picture?
Yes.
Yeah.
Good idea. Done.
It's not faster.
Yeah, I mean, okay, follow me, let's go.
Those are we go through what they call a yes.
Well, just they are meeting. And with the one.
Oh,
Really big.
yeah.
They got like big new type stuff. They got occasionally like you got a trail mix. I don't know. They're hanging at the bottom. You do a machine.
What?
Yeah.
I know.
Got back early, huh?
Yeah, exactly. So there are definitely people that were like hovering around, like this seems to be the obviously stolen. Yeah, I think. If you like. You work on it.
Yeah, not quite. So we use, we do a little bit of development of the theory of machine learning of AI for example, for getting the masses.
Yeah.
But we started mostly on condensed matter physics.
Oh, yeah.
Right. So Yeah, so topological stuff and trying to create field waves. We also do super heavies, but you're usually nice products.
So I included one, or, have you ever partnership here, recently?
Oh,
Maybe.
the helium thing?
Yeah, they do it on.
No, but I know, I collaborate with the experimental physicists with those that. But no, we do quantum computer algorithms.
Yeah.
But we don't build the quantum computer. We spend computer algorithms and we also try to develop qubits, right? For qubits from condensed matter. For states again, super heavy atoms, like heavy molecules.
So actually, I do have an interesting quantum computing that I've been looking to all because actually, Stuart Kessler, he was mentioning how there was I don't know if I'm saying the name right, Majorana's fermion state at UCSB, where they're facing that. I'm not sure how far they've gone. I've learned a bit about it, so it's all these seem pretty important. Because you're trying to preserve a state, right?
Correct. That's the main reason.
Yeah.
And I think that one, there is a claim that a computer from what say Microsoft or Amazon, but it's based on Majorana.
Microsoft.
Microsoft, right? Yeah. But there's a lot of debate because they have not been publishing it. Nobody knows if it's true. But yeah, the main thing on Majorana is that it will. Because it's a topological state, those things they are affected by a lot of interactions easily.
And more than still in Norway. Yeah, but did you come here? It's mostly there now. Yeah, for that specific day, packed by people celebrate.
Yeah, it's just. It's hard to calculate them though, so we developed the last 4 to 5 years a way to calculate.
Very protect and talk.
So, if you want to develop the code, and the basics, so we probably have some things here. So, you can apply that kind of research for a lot of molecules or videos.
Okay, how, so, in terms of it would be useful, but try and apply some exception as well, where you have some general representation, I guess. Or the system be more what we kind of assume like different, say, instead of retraining your.
And so in the capital
Trying to learn
Berkeley National Lab,
representation.
they have a very cool, flexible quantum computer, meaning that they can, upon request, they can try your architecture like you're asking them. It's small, it's not like the IBM.
I don't know if this is what you're asking.
Probably has like.
Don't make the question that I think you're asking. Anyway,
It's like you design your own architecture, and then we'll do it for you first, and then you can test the algorithm.
Just when